Alright, let's get started with the second problem of the day, which is going to be this one. This is LeetCode number 735, Asteroid Collision. You are given an array of asteroids of integers representing asteroids in a row. For each asteroid, the absolute value represents its size, and the sign represents its direction, positive meaning right, negative meaning left. Asteroid moves at the same speed. Find out the state of all the asteroids after all collisions. If two meet, then the smaller one will explode. If both are the same size, both will explode, and two moving in the same direction will never meet. I see. Interesting. Well, let's see. 10 to the 4 seems to indicate O of n runtime, or somewhere in that ballpark. So let's actually just clarify the question first. So negative implies left, positive implies moving to the right, and the numbers represent size. And we want our output to be the final state of the asteroids after collision. Okay, let's see. So if two asteroids move in the same direction, they will never meet. Likewise, if two asteroids move in the opposite direction, one or both will be removed. Okay. Let's see. If they move at the same speed, what happens if we have, let's say, an asteroid in the middle and two asteroids coming towards it? Well, I guess in that case, we can kind of assume that, like, for example, what if we had -5, 5, -5? Well, this is moving to the left and this is moving to the right, so it doesn't matter, right? So in that case, So first two will never collide because they are moving in opposite directions. And then the second two will collide and both are removed. So that leaves us with -5. Because this will move to the right, this will move to the left, and they will collide. And then, for example, let's do just a random example with 10, 2, and 5, or yeah, 10, 2, and -5. So 10 and 2, so no interaction between 10 and 2. Then we can say -5 from here because 2 collides with -5. -5 stays. Then we have 10 because now 10 collides with -5, 10 stays. Interesting. So I guess the idea is that will I have a situation where, is it possible for a collision to happen right to left? Or sorry, left to right? Because it kind of seems like if we have a negative value here, it collides with you and it collides with you. So it seems like we might be able to get away with a sliding window, and I know sliding windows, negative values, but this time the negative values don't matter in the context of like the answer to an extent. Like they don't matter numerically. So I think we're fine. Um, but the idea is that we can have one that's moving to the left and one moving to the right and they'll collide. But we can't have a situation like this where we have one moving to the left and then one moving to the right of it, because then it doesn't matter. Is there a situation where that could be incorrect? No, because if we swap them around and we had one moving to the right on the left side and one moving to the left on the left side, then, oh, now that I think about it, what if we did like, what if we used like 2 pointers? So like if we did like a 5, -5, 10, -10, and we said we did a left pointer here and we did a right pointer here, and we said while left is less than right, for the left side, compare to see if we need to remove some item, and then for the left or for the right side, compare its next value to see if we need to remove one or the other, right? Or like we would add it to some final array, I guess, to in that sense. That kind of sounds interesting. This would be an O of n runtime, probably O of n space, just so we can remove things quicker. So what I imagine is that we do a convert int array to linked list, then back to final int array, in order for the size to be actually the same proper size. Let's see. And then move the left and right closer to each other. I mean, that works. Well, only if we have a collision, right? Or only if we have one of them explode. I think so, yeah. That might work, because if we had a right and a left, yeah, like this, then we'd have a collision here, and we'd skip both. And have a collision here, and we'd skip both. Yeah, maybe. Okay, I think I'm seeing it come together now. So the left side logic is, and the right side logic is pretty much the same, except that we just need to determine like sort of what survives a little bit differently, because for left side we're comparing the next value, and for the right value we're comparing the previous value. I think that works. Let's go ahead and code it up and see where we end up after that. Let's say var left is 0, var right is equal to asteroids dot size -1, and we kind of need a linked list. Let's see. Do we want a linked list? How do we, at what point do we add the values into our list? At what point do we add values into our list? Because we get the candidate, maybe one of them explodes, maybe one of them doesn't. I think the time where we add them is if we know for sure that it's quote unquote safe with regards to no, but there's no way to know that it's whether or not it's safe, right? Is there a value that is not used here? Okay, so the asteroids only go from -1,000 to 1,000. But oh, and the asteroids cannot be 0. Maybe we just set unused values to 0 and then go back at the end of the array or at the end of the iteration, because constant multiples don't matter, right? Constant multiples of big O runtimes don't really matter. So we could go back at the end of the array after we've solved all the collisions and go ahead and do that. Yeah, I think that works. Let's see. Now I'm just thinking, like, would a two-pointers approach actually work? Because I'm thinking of, like, if we had something like 5, 5, and then like -10, -10, or we'll do 10, -100, right? In this case, if we had a left pointer here and a right pointer here, this would go, because this 5 and this 5 doesn't do anything, then we would move it to the next pointer, or actually the pointer afterwards, which would be 10 here. And then because this -100 would beat this amount, then we would set this we would set this in the return array to, or we would override maybe this variable completely, right? We overridden to -100. So maybe maybe we do one pass on the left and one pass on the right. One pass from the left and one pass from the right. Let me think. Yeah, we could do that. And then one final pass from, or to move to array. So if we wanted to do that, then we could do asteroids for each. Actually, we can't do this for each loop because then Kotlin will yell at me for concurrently modifying an array. So we'll do for index in 0 to asteroids.size -1 because inclusive. Actually -2 because we'll be going to the second to last. We'll say val next is equal to asteroids at index +1. And then we'll say, so this is the left to right resolution. We'll say if asteroids at index is greater than 0 and next is less than 0. So current moves to the right, next moves to the left. Then we want to set our value to so that our we either keep a survivor or we don't keep any survivors. So maybe we move our index outside, and then we say while index is less than asteroids dot size minus 1, and then here we do index plus plus. Otherwise, if our index is going to the left, then it doesn't matter. If our index is going to the right and this one is going to the right, then it matters. If both of them are going to the right, then it doesn't matter. Else if asteroids at index is less than 0 and next is greater than 0. So moving in opposite directions away from each other, because our current is moving to the left, our next one is moving to the right. Then we do index plus plus because we want to increment over the next one, and then we want to increment to the one afterwards as well. Here we want to say that our asteroids at index plus 1 will be equal to the max of math.absolute value of asteroids at index. And well, our current value is greater than 0, right? But we need to do the math.abs for our next value. And our asteroids, our val temp is going to be, or we can just say current, right? At index and current. And then we want to say our asteroids at index is equal to 0. And 0 is how we know that it doesn't matter, essentially. 0 will be our ignore value. So the idea is that we resolved all the collisions from left to right first, and then afterwards, we resolve all the collisions from right to left for any of the remaining asteroids. And since we increment our index at the bottom, then we don't need to do that there. And I think, will that type of resolution work? Because if we had a situation like this, or like if we had let's say that we had like a 5 into -5 into -10, what it actually is the end result of this? Because, or actually no, because this would collide later, right? From right to left. But what if we did something like the opposite of that? So we did let's see. Could we do the opposite of that? 5, 10, and -1, right? Compared to like 5 or 1, -5, 10, -10. So in this case, the asteroids would collide left to right. Fine. And then in this case, they would collide almost right to left. But I guess it doesn't really matter because the closest values will always collide first. The closest pairs will always collide first. And so to a certain extent, I don't think actually it matters that much that you're doing this like sort of sequentially, like left to right and then right to left. Because you'll still like take care of all the pairs first. Though I do wonder if a simple right to left and left to right resolution would be enough. It'll be interesting. And then we set index to asteroids dot size -1, while index is greater than or equal to 0. Or actually strictly greater than, because we want to do val current is asteroids at index, val next is asteroids at index -1. And if current is going to be less than 0 and next is greater than 0, then asteroids at index is equal to 0. Asteroids at index -1 will be equal to the max of our absolute value of our current as well as our next. And otherwise, if our current is greater than 0 and our next value is less than 0, then we want to increment the next value and do that. We could also do a while asteroids to a var inner is going to be equal to index -1, while asteroids at inner, or inner is a keyword, so we'll say inner index to make it more clear. While the inner index has a value of 0, we want and our inner index is greater than 0, then inner index -. The idea is that we want to just keep on going until it's 0, or rather we want to avoid like processing collisions with zeros in them because they don't matter. And I think we're gonna do something. Well, we don't need to do something similar for the first iteration because we know for sure that in this iteration it doesn't matter because we won't have any zeros that happened before, or we won't encounter any zeros essentially. This left to right resolution will only be creating zeros. Right to left resolution. And then we can say for asteroids for each, and var return list is a mutable list of integers, and for each number within asteroids, if num is not 0, then return list dot add num, and then return list dot to int array. And let's go ahead and give it a shot and see where we end up. This needs to be inner index. This is Asteroid size -1. This should be fine. I don't know why it's not fine. At index, because we set the index there. Oh, these should be minus minus and not plus plus. And if current is equal to math.absolute next, then what we want, then asteroids at index +1 will also be 0, and index plus plus at that point. And same thing here, so if next plus, well, we'll just do the next equals math absolute value of current is then asteroids at index -1, 0, index minus minus, and actually we can put this in like this and do an else right here, and let's move u down, and we do the same here. Similar sort of thing here, where if we have the same values for both of them, then we set the next value. So we set both of the cells respectively to 0. Otherwise, we set the cell of the next value to whichever one survives. And we can do the negative version of, well, and if asteroids at index +1 is equal to math.absolute value of next, then asteroids at index +1 is equal to negative asteroids at index +1. The idea being that since we're taking the absolute value of this, we kind of need to also make sure that that part is accounted for in terms of if that negative value is actually what survives, then we need to actually set that value to the negative, because that's the one that actually survived. This should be index -1. I forgot about that. And let's see where we end up. Looks like it worked for the first test case, but the first test case may not necessarily have a lot of edge cases. Looks like we messed up with this bottom one, 10, -2, and 5. We somehow ended up with 2 values of 10. Let's see. 10, 2, and -5. If we do right to left resolution, you don't do anything. 10 and 2 don't collide. Then we do 10, -5. 2 and -5 leave -5. Though technically it will be 10, -5, 0, right? Or it'll be, sorry, 10, 0, -5. Then we do here, I guess you're right. These should be all set to inner index, so that we don't override any values that we don't care about. And the same thing with this one. Well, actually, no, not same with that one. Again, we are not producing or we are not consuming zeros here. We are consuming zeros on the right to left side. So now our inner index should go until either it hits a non-zero value or it reaches 0, at which point we don't really care too much about it, because this won't trigger because next is not greater than 0. Then it's not less than 0, it'll just go down, and then it'll just continue until the end. So I guess if inner index is at 0 and asteroids at inner index is still 0, then we just want to break out of this, assuming that that break works. Because the idea is that if we hit this point, then we've resolved everything and we don't need to continue again. Ooh, are we gonna actually hit it? No, was that just slow? Guess it might have been just slow. Yeah, so now the inner index will go to here and here, and it'll compare the -10 and or -5 and 10, and then that leaves 0, or like that. So 10 and -5 leave 10. I am a little bit concerned about this though, this inner index sort of iterating like this. We'll say inner index starts off at index -1. And then for each instance, we'll say, actually we don't need to remove that. We'll say our inner index is equal to the min of either index -1 or our current inner index. So the idea is that if we're at an index that is already lower, if we're at an inner index that's already low, then we don't care about setting it to like the index -1 and then going again. Because we've already, if there is a distance between our current index and our inner index, then the inside part is just all zeros. Because otherwise the inner index would have filled them in, right? So in that case, I'm starting to wonder if whether or not there could be a way to further improve on this. It doesn't feel quite as efficient enough. Min of index -1 and inner index. I think that's fine. I think we're fine here still. Let's go ahead and submit it and let's see where we end up. There are probably some edge cases maybe that we haven't quite considered. Let's see. 2, -1, or -2 and 1 and -2 and 1. Let's see, if we did a left to right resolution, then that doesn't do anything. The 1 and 2 collide. So -2, 1, -2, 1. So first -2 and 1 don't do anything. Then we get to -2, -2, 1. 1 collides and -2 leave -2. If you're going left, you're going right. We do care about the next instance. Okay, so in that case, I think we could do that instead. And same here. We don't want to ignore any of the pairs then. That's happening. Might be a little bit slower, but that should work. Yep, that works. Let's go ahead and throw the submit again. Yeah, so initially it was just that we were skipping over it. Ooh, okay. Larger answer, still incorrect. Let's see what's going on there. So 7 and -1 don't collide. 2 and -3 collide. So -3 collide. Then -3 and -6 don't. Neither do all these. Neither does the 4, sorry, or 10 or 2. Then working from the reverse, 2 doesn't collide with 10, neither does 10. Neither does the, well, the 4 collides. The 4 collides with the -6, so that leaves -6 there. No, the 4 doesn't collide because that's going to the right. -6 is going to the left, right? So these don't collide with each other, obviously. And then the 2 and -3 did collide. Two and -3. Let's see. Where did the collision happen? Because it seems like something isn't right. This 4 is going to right, 6 is going to left. No. This 2... Oh, this... Okay, so you collided there. So you should be there. So you collided like that. Sorry. And then you collided like... Oh, I see. So then I set it to... Let's redo the left to right collisions, because I don't think I actually did it properly. So 0, 7, 2, -3, -6, -6, -6, 4, 10, and 2. So you collided with the -1 and that worked. You don't actually do anything. You collided. So 7, or 0, -3, -6, 4, 10, 2. Yeah, that's the problem, because then you actually stay as a 0. And then we move you on to -3 and then -6 and onwards, right? So at the end, we don't actually collide you with everything that's possible. Yeah, this one is confusing. I feel like, again, like we had like a decent like half solution, but there's just some nuance in here that just doesn't make it work. But it's 39 minutes in, so let's go ahead and take a look at the solution and let's see where we end up. Okay, so our original intuition of doing things like, oh yeah, like Does it, could we just evaluate it in one direction? Kind of was, in a sense, a step in the right direction, but not quite. So the idea is that we build up a solution slowly by adding in asteroids one by one and seeing what the result of those are, essentially. So we start at the left side and we build up in the stack. And the reason why we use a stack is just because we get the most recent asteroid on the right hand side. So that's why we use it. And the idea is basically when we have a new asteroid candidate to put into the stack, we evaluate all the collisions basically from right to left until it no longer collides with anything else, and then we insert it into the stack, and then we continue like that. And so the idea is that after we evaluate all the items within the stack, or at least until it no longer collides, then that what is left is fine. It's stable, essentially. And we don't need to bother with manipulating it any further. So after we build up our stable stack, once we add all the elements from our array into our stack and get the final solution, we build up a result array, and we go from the end to the beginning because the stack is last in first out, so it's the one on the top is on the right side, and then we slowly go down from there and we just pop all the elements, move them into our array, and then we return that array. This runs in linear time and also uses linear space because we need to use a stack. I'm a little bit frustrated that I didn't get this, but hey, that's just the nature of how things go sometimes. I think that this is a pretty intuitive solution now that I think about it. Though I don't know exactly what's the pattern to really identify here for future reference. Like for the previous problem, I could say, okay, if it feels like a sliding window problem, but there are negative values that actually matter, then we can say that we use a hash map instead. That makes sense. We've seen that two times now. But something like this, I'm not sure if I've really seen this before. Using a stack like this and building up a solution. Maybe I have, and maybe it's just been a while. I'll have to look through my previous solution and see if there's really been a solution or been a problem that uses a similar solution to this. I can't think of any off the top of my head, which I'm not sure if that's a sign that I need to go back and do more review, or if this is actually something that's completely new and something that I really haven't seen before. But that's basically the solution. So we go with the stack, we build up one at a time, and then evaluate essentially as we go. We resolve all the collisions as we add new items into our final collection, and then after that we move our final collection into the array that they want. In any case, I hope you learned something, and I'll see you for the next problem.